Hello, everybody. So, in my O5 section, there was a computational error that threw off the results on the theoretical chi-distribution that I was working with uh, the other day. And it's because when I was generating the expected value, I hit the row total from the above row. So I just want to go through an example real quick if I can. You'll find out that our degrees of freedom are 1. I'll show you how we get that again. And then the 3 values that we use for alpha, our level of significance, are 0.10, 0.05, and 0.01. That's specific to our class. As you can see, there are other ones that get chosen. So the critical values, or the multipliers as you guys would know them as, are 2.706, 3.843, and 6.637. I hand one of these out in class so you guys can have this. So here's what we worked on. We were talking about, do dogs respond to vacuums being on or off? And so and the idea is if you pull out a vacuum and you kind of travel around the house, does a dog care if it's on or if it's off, if they see the vacuum, so on and so forth. The null is the proportion vacuum yes, the proportion vacuum no. They're equal. We're really simulating multiple proportions. So you could say all proportions equal, and this thing's counterpart would be at least one is different. If you said independent, then you'd have dependent. If you had no relation, this would be relation. So if they're not equal to each other, then you'd have some kind of relationship going on. Your book tends to lead this way. I've seen other authors listed in this type of format as well. This piece right here is referred to as your chi-squared test statistic, and I'll show you how we get there. First of all, this is our data. Vacuum on, yes or no, and dog reacts, yes or no. This is our explanatory, and this is our response. To get this expected value, the 9.4, we take the row total, which is 34, and the column total, and we multiply those two, and then we divide by 87. That'll give us the 9.4. To get the expected value for this cell, we take the row total, 34, multiply it by this one's column total, 63. We multiply those two together, divide by 87, we get that value. For the expected value in this cell, we're going to go 53 times 24, and we'll get 14.6. 53 times 24 divided by 87 gives you 14.6. And then the last one's 53 times 63 divided by 87, and then you get your 38.4. Now, what this is saying is if all things were balanced, that's the value that it should be there, or should be in there. And then what we do is we take the observed value, 14, minus the 9.4, observed minus expected. We're going to square that. Effectively, it gets rid of the negative. And then we divide it by the expected, 9.4. Now, I'm going to make a comment. This is essentially a z-score. You just don't see it in that formula. And the reason that I'm saying that is when we look at the applet, there's going to be this z thing that pops up. We ignore that. We won't use it. But there is a connection between the chi-squared distribution and the z-score. Anyhow, so you're going to do the same observed minus expected. So you observed minus expected, and you're going to square it, divide it by the expected, and so forth. Now, I end up getting 5.3189, and I'm rounding off, so that's going to create some error. So when I do this, from the applet, I actually get 5.16, and I get 0.023. Let me pause for a second. How did I get my degrees of freedom? Well, we look in the center, or in the body of the table, not the totals. And we have 2 rows and we have 2 columns. So the number of rows minus 1, the number of columns minus 1. So we have 2 minus 1 times 2 minus 1. That's where we get our 1 degree of freedom. And on that table, that's where we get our 1 degree of freedom. Now, the 0.10, the 0.05, the 0.01, those are the common values that we've been using for our level of significance, our alpha. So what I did was I said, well, what's our critical value if alpha is 0.10? Well, it's 2.706. Critical value for alpha is 0.10, or 0.05, I'm sorry, is 3.843. Critical value for 0.01 is 6.637. So you would know this as weak evidence against the null, moderate evidence against the null, strong evidence, and then very strong evidence against the null. And that's the same thing with our p-value. Our p-value is 0.023. It says we have strong evidence against the null. Location of the test statistic is in between these two critical values. And so, these two critical values, which are generated by these two alphas. All right. That's the strong evidence region, strong evidence p-value. Okay, so we have strong evidence against the null. Now, how do we make this work on the applet? So I'm going to do a couple of things. So first of all, explanatory variables, response variables. There was a question that popped up about, well, how do I make a 2x4? Well, apparently we can't. And so what we have to do, and this is what you would have to put in the table. Let me do something. When you're looking at this right here, this should be what this would look like if you turned, I'm going to regret doing this, I think. You turn that off. So you want to have all of that stuff typed in. And you can have multiple reactions. I'm sorry, I said that wrong. You can have multiple explanatory variables. So you could have vacuum on, vacuum off, vacuum rolling, and that kind of thing. So you have to just list all of the possible explanatory variables that could occur. And then you have your two reactions as successes and failures. Let me click this back over and we get our data back. So that we can get to our chi-squared value, we want to click down here, show chi-squared output. It'll give you a breakdown. It'll give you the actual sum as they've taken out to multiple decimal places, and then they'll give you the actual p-value as well. Okay, let me just scroll over here and I'll just make this comment. So if you do the z-score based off this, you get some slightly different things going on, but what we're going to focus on is we're going to use the theoretical. So we're just using these values here. So we don't really need to click the shuffle. All right, I hope that helps. And where I made the mistake was when I created the expected value chart. You're supposed to get, for this number here, you're supposed to go 53 times 24. And what I did was I went this number here times this number here by mistake, and then divided by 87. So it actually generated a different result than needed to be there, and that caused some ripple effects, especially when we were working with the app. Hopefully that helps. I'll talk to you guys.